welcome to our class, Computer Vision, and I hope that you can hear my voice and see my video, and also my share screen. If you find anything wrong, please try anything to let me know. Okay, so today is our first class, and let me make the full screen first. Okay, and during our class, I will record our lecture video, but I'm not sure every lecture will be shared online, but we will do video recording just in case someone need it. Okay. Okay, so let's start our class. And again, if you find anything wrong, either the voice or the share screen, please let me know. Okay. So I hope that you didn't go to a wrong meeting room. Our course is computer vision, and I'm Chen Ling from College of Computer Science, Computer Science Department. Yeah. And wait a second. And our official lecture will supposed to be told on EC 114. And however, as you know that due to the academic, pandemic prevention, so so we have to move it to online, and so we are supposed to have 2 hours in class physically in EC 114, and they are supposed to another 1 hours for asynchronous video. Actually, this is the new rule from our school. I guess some of you have may heard why it become this way. So you probably know that for say NCTU, the former Jiao Tong University, and we usually say our official course supposed to be such as 2CD, 4G, or something like that. Yeah. And however, on the other hand, for our cooperative school, currently we will merge Yangming University, and then usually do such as Tuesday 2, 3, 4, right, and something like that. Yeah. And so two schools have to figure out some way to mix and cooperate pretty well. So our brilliant, say, office of teaching affairs, and they say, okay, perhaps we can do this to merge well because two school or two campus didn't willing to move to another way. So then you do a compromise solution. Say, okay, we can do 2 hours, and that is in personally, yeah, in person. And we also have 1 hours for synchronous video. And because due to our college's instruction, so for the first week, we were told online, and I guess for these 2 weeks we will we will teach our class in say continuous 3 hours. But this is the first week, so we will not teach 3 hours in row, right? In row. So and this class is a grade J level class, and we also welcome such as students from the senior levels, undergraduate senior level. And so, but you have to have some essential skills or capability. The first one is you have to, because we will have around 2 or 3 homework assignments, and we will also have one term project. So you have to possess sufficient programming technology. And the current in the last my last time teach computer vision is around 2000 and I guess 17 or 16 or 17. Yeah, and we use C and C++ well with OpenCV. However, recently Python is more and more popular, right? And our TAs could provide Python simple code for your homework. So anyway, so we and if you have familiar with you are familiar with C plus, it is quite easy for you to transfer to Python. So our homework could be Python or C plus plus. And in this course, we will because we have to process some image and or even 3D structure. So you have to possess some knowledge, at least the moderate level about the data structure and the algorithm. Yeah. So, but we will not use a pretty complex data structure or algorithm. You at least you have to know the sorting or multi-level array. I think that is sufficient, and also linked list. Yeah. And because for computer vision belong to Institute of Multimedia Engineering, and so you know that for multimedia processing, we usually use a lot of calculus and matrix computation. For instance, for student in our campus in computer graphics undergraduate, you have known that everything will become a matrix, right? So you will have to have some essential knowledge about calculus and the metric computation. And there are also some related related courses quite close to computer vision. For instance, such as the computer graphics, image processing, and the pattern recognition. Yeah. So, uh, so if you have learned some idea from other course, it will be helpful for your learning in computer vision. But it's not a requirement or it's not compulsory because it's just optional. It will be better, but it will not say differ or make your learning difficult. Yeah. And let me talk about myself. I am the teacher in this course. I'm Yichen. Chinese name is Ding Yichen. And my background is actually I'm a graphics and doing some region related work. For instance, for my PhD thesis, I was doing some such as motion capture. Mocap means I track someone's face and transfer their facial motion to animation. And recently, we also doing such as market tracking for such as VR, AR, yeah, and not AV, sorry, AR, VR. Okay, and so I'm not a typical computer vision guy. So, but I guess my teaching orientation would be more application oriented, and but we will also teach you some essential concept. So if you find you want to know something for some specific topic, perhaps you can let me know and we can discuss. And my office is at the EC 704. If you want to discuss, find me. The first priority or the most easiest way is through email. And yeah, so that is my background information. And so we have currently we have three TAs for this course. And then Fu Xingyu, Tu Zhongqian, and Lin Yucheng. And the office is at EC 229B. And you can again, I think the first part, the first choice for you to find here is through email. And of course, you may have some chances to do demo with the TA. So our TA's office is at the engineering building 3. Yeah. And so for this course, I know there are a lot of people because currently uh, our upper bound for this course is 19th, and I saw that yesterday there are still a lot of people queuing on the waiting line to enroll this course, and at end of this course, we'll talk about the ed class problems. And for those who have not yet enrolled in this course, we have temporary announcement pages. And however, our official page is still at eStreet. And this is the QR code for our temporary announcement pages. And about the textbook, uh, actually, computer vision is quite uh, is highly progressive and highly updated topics and quite hard recently. So we still have the textbook, supposed to be this one. So that is the by David Forces and Juan Bons from France, and David Forces from UIUC. Then have a textbook called Computer Vision: A Modern Approach, and I encourage you to. If you like to study something, I encourage you to buy this book because although the author still needs some support, right? And however, if you just want to check some ideas or check whether this book is good or bad, perhaps there are actually some electronic PDF you can search that online. But yeah, but I still encourage you to if you think that is good, and perhaps you can buy one. And you can use either the first or second edition. The first edition is from 2003, and the second one is from 2012. Okay. And so that is the textbook. And of course, there are actually two versions for international student and for United States. So their covers look slightly different. And we also have the reference book from uh, Richard Zelinsky, this one, but we only have partial content from this book. Yeah. And because I think we will use, say, a half of this book. So the content, for instance, for this course, we will separate in two parts. For instance, the first two-thirds, we will talk about some uh, traditional or conventional way for computer vision. That is before 2012, 2011, right? And I think most of you have known that after 2012, we will become the computer vision involve more and more deep learning technology. So I guess for sure, or on about one third or one fourth of this course, we'll talk about some recent ideas about using deep learning for computer vision. Yeah, and so if you are pretty interesting or you want to focus more on using deep learning for computer vision, there are actually a lot of different or there are other courses about using specific deep learning technology for computer vision. Yeah, so in this course, we still have to provide you some essential concept to the modern idea. Yeah. So for the earlier part and or the classic part, we will use the textbook. However, for the later one, we may have to include some reference. So for computer vision course, not course, the research, there are two, you can say the best journal is the PAMID, IEEE Transaction on Pattern Analysis Machine Intelligence, and also IZCV. So there are two uh, journal or top journals in vision field. Of course, there are some other good vision journals. Yeah, and so there are also some uh, popular or the top conference in computer vision, such as the IACCV, CVPI, CCV, and in addition to those popular journal or conference, and there are some related. You can also find some good or top work from some related journals, such as or fields such as transaction image processing, multimedia, or if you're doing some video coding, there are CSVT. And a lot of our slides will from some reference lecture, such as the UIUC's computer vision course, or MIT, Georgia Tech, UBC, and CMU, and others. Okay. And so, what is the computer vision? I guess because you attend this course, I guess you have some idea about that. Let me quote some famous sentence. For instance, in 1982, the Johnson Marr have a quote about the computer vision. His idea is that about vision, not just the computer vision. So if you want to know to discover something from your image and what is presenting the world and where the things are and what action are taking place, so you can think about it. Your input could be some image, right? And you will have to find what is in this world, so you can say that is your object here. And you have to find where they are, so that is their object's position, right? And because in this world there are actually could be some interaction or some not only interaction, sometimes you may see a sequence of image that is video, so we can observe some action. So that is what computer vision do is try to analyze some contents from the image. And there are several closely related fields such as image processing or artificial intelligence and machine learning. Yeah, machine learning actually belong to a branch of artificial intelligence, right? Yeah, but is a big trend here right now, and just as opposite to computer vision, there is a reverse work for reverse field, that is computer graphics. We will talk about what's their difference, and whenever we apply the computer vision to some human interaction, we may touch such as human computer interaction. And if we would like to detect some real world to enhance some information, so that could involve such as the augmented reality or the virtual reality. Yeah. So let's take a look at what is the difference. I guess some of you may see these figures in my computer graphics course. So what is the main difference between computer vision and other related work? And there are two related fields. The first one is image processing. In Chinese, that is 影像处理, right? So in the image processing field, for instance, the famous Lina, you will see, for instance, we may use whenever you use such as Photoshop in some camera or image enhancement application. So, for instance, given a photo of Lina, and perhaps we can enhance their age and make them slightly beautify, right? And so that is usually image processing field good. And for computer vision or pattern recognition course, we may have to find, for instance, given this image, we will find some features. So just as the Mars 1982's quote, and our goal is try to analyze the content within this image. So perhaps we have to figure out what whether there are some important features, such as eye corner is an important feature, or the lip corner is an important feature. And afterward, perhaps we can check whether there is eye here, and whether there is a nose here. And when we compose eyes, nose, and the mouth, and we may think, okay, this one supposed to be a face. There's supposed to be a face over there, and perhaps we can compare to our database, and we find that okay, this female, this beauty could be, say, uh, Lin Zhiling at 24 years old. Yeah, this could be 20 years ago. Yeah, and so there's uh, another field that were in opposite direction. So that is computer graphics. So for instance, this is me, and for computer graphics guide, then usually given such a 3D model, then graphics guy will try to synthesize to make the image look like the real thing. So that is the difference between computer vision and computer graphics. But these two fields sometimes or half of time will involve 3D information, right? So we have something in common, such as the representation for the world. These two fields use rotation and translation, and they are also such as the camera projection. It's a common for the field, but the purpose is different. This one is for mainly for synthesis, and this is one mainly for analysis. Yeah. However, this three field is recently the border between these fields is gradually or more blurred, become more blurred. Because whenever you want to analyze something, perhaps you can rely on some synthesis technology. And for instance, if you would like to build your model, perhaps you have to check something from your image, right? And some of the image processing technology can help us better analysis the input image. Okay. So this is a conventional way to describe these three fields. So if your input is a description such as 3D model here. For instance, you have some 3D model here, and for instance, that is a teapot here. And given this teapot, you will try to generate some image. So that is usually belong to computer graphics. That is 计算机图学 in Chinese. And if you given an image, you hope that your output is enhanced or processed or abstract image. So then usually used to belong to image processing. However, currently these two fields also did some image in and image out work. And for computer vision, is or a conventional definition is given an image, just like Lin Ziling here, and we hope that we can detect his eyes, nose, and find his face, or from a big picture here, can find the Lin Ziling is over there. Yeah. So that is the conventional definition for these three fields. And so this is another figure to tell the difference between graphics and computer vision. For instance, given a definition here, a description here, and given a model here. So for instance, this is a camera here. Yeah. So in this word, in this course, we will see a lot of camera just like this one. Yeah. So given the model here, we hope that we can generate an image that look like those model realistic or non-realistic shown in the camera, right? And so for computer vision, its idea is just look sort of like the opposite or reverse direction of computer graphics. That is, given the real things and given this camera, real camera, we hope that we can generate the corresponding model or description. So that is the main goal of computer vision. Yeah, and however, computer vision actually is one of the most challenging field in computer science. Yeah. So why should we say so? Because, for instance, this is a figure. I guess most of you can easily recognize that. Okay, there is a path here, and we can detect some tree here, and we can also uh, predict their depth, such as this is closer and this is further, and this tree is far from your location, your eyes, right? So that is quite trivial for a human. However, if you especially for student that first time process some computer vision task, uh, then we'll find out that okay, it's not that easy to, for instance, reconstruction the world or recognize those trees. Even though we have deep learning to date, sometimes we may not uh, to reach the capability of humans is not very easy. In some texts, computer could be better than humans, such as photo recognizer, or especially for special category recognition, such as dog recognition, cat recognition. Computer can do better than human. However, for some general scene analysis, human is still almost sometimes still better than the best vision work. Okay. So let's talk about why computer vision is difficult, or what is its challenge. So for computer vision, our input is the image here. So that is our image, our input image here, right? And so here is our camera here, and so we usually show a film here or a picture here that usually represent, for instance, our film or the CCT, the CMOS here. Means you can get some ray from the real scene, and you can uh, produce your image through by the CCT and the CMOS. And so why the computer vision, I say, is challenging, or sometimes it's even ill-posed. Yeah. And let's take a look at an example here. For instance, if you have a film here, and here we have a spot here, red spot, red spot, red spot here. So given whenever you only have this single input image, the geometry of this image could be a ill-posed problem. So, for instance, if you have a point here and one solution is say given 1 meter distance, you have say a red point here that is around say um, 5 5 centimeter. Okay, in its diameter, its radius, right? And it also could be there are actually infinities or infinite possible. Another possible solution could be say for a distance 1.2 meters, and there is a slightly larger point or spot here that is cm in radius, and for 2 meter, it is also possible have a spot with 10 centimeter radius. So it means if you only have a single image, sometimes a lot of work is ill-posed. Ill-posed means there's actually no single solution. There's sometimes have infinite or possible solution. And so let's first keep taking a look at why we humans, or why a good vision work can't estimate the thing better. So so let's go back to humans. So we humans actually is a deep learning technique, just like you have born 20 years ago, right? Or more, or fewer, 20 years ago. So your brain is say a neural network, not artificial. It is a natural neural network. You have trained your assistant more than 20 years, right? So during these 20 years or more, and you actually has learned some prior knowledge. Prior knowledge in Chinese, it could be say prior means 事先先辈资料, some not the 旺旺先辈, okay? So but there is no formal definition in Chinese, okay? So 先辈知识, okay? So we human actually have a lot of prior knowledge during when you train your brain within these 20 years or more. And for instance, given this figure, sometimes we can actually conjecture what is for instance, you can say, okay, this one is closer, and this one could be further. And that is because you may have some prior knowledge about a whiteboard or a box, because you usually have see a board could be, say, 1 meter by 1 meter. You can you have some prior knowledge about the size at certain distance, right? So this is one possible prior knowledge. And we humans sometimes also can tell the 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 front or the far or the order according to occlusion. For instance, in this case, you may say, okay, this one is closer, right? And this is in between, and this is farther. And that is because you have your prior knowledge. You say, okay, that is the box over there, or the square over there. However, it also can have a plane there. Another possible is that we have a plane over there, and this is a single plane. And perhaps we paint some color, some box, not box, some box here, and we will paint some other pattern over there, and it just look like some occlusion between squares. However, this could be in geometry, it could be a single plane. Okay, single plane. So 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 that is the difficulty for so-called the monocular computer vision. Monocular means you only have a single view, single eye here. You have to rely on some prior knowledge. Yeah. And because we have taken a look at a lot of in our real world, we actually live in a perspective world. So for a box, when it's closer to us, then we will be slightly larger in image, and the further will be foreshortened. So we human can recognize the orientation, or guess the depths of this box. And there are also some other perspective phenomena, such as the fog or the mist. Yeah, and can also help, because of farther, if for the far mountains, it will be partially not occluded, the trans, opaque, or partially transparent, sorry. transparency will be influenced by the fog or mist, right? Okay, so that is so this is an example. So when we human will to recognize a thing, we actually rely on a lot of prior knowledge here. And another possible is that lighting. Yeah, so this is a teapot here, and we actually can rely on our knowledge about continuous surface. For instance, a surface here, and in our chapter 2, we'll talk about the reflection. That is something common in computer graphics. And we whenever we see this kind of smooth transit gradient in image, we will recognize that, okay, it could be a smooth surface and is slightly bump out, right? And again, we can also rely on shadow to predict how height or how far is this square from the floor, and also such as from texture. This is actually the same bolt, but we change the texture, we will see totally different. The perception for human will be totally different. Yeah. And in addition to, so that is a single, monocular viewed. Monocular means single view. We static Q. Static means we only have a single image here. And however, for dynamic scene, dynamic or dynamic Q means, for instance, you are sitting on a bus and you take a look at outside of your window, and for instance, when you see here, you will see a pillar over there, and when your car is moved to here, you will find your the your pole or the pillar move faster than the far scene. So that is because we have so-called a motion parallax. Because, for instance, when you see here, you take a photo here, and for instance, this is your eye here, and you will find the in your image here. So let's take a look at this image. Your image here, for instance, this is 0 to 640, and the background point here could be behind this this pole, and it could stay at 240 here, and the pole here could be, say, or stick here could be, say, 120. However, for the closer things or a closer stick here, it could move faster. Perhaps it could move to, say, 400 to the in the image here. However, the farther world will just move to 300. Yeah. So so this is another thing. So we human can rely on this kind of so-called motion parallax to estimate the depths. So this is another cue. So actually, our computer vision sometimes have to rely on this prior knowledge to help us analyze this kind of thing. Yeah. And if because we human have two eyes, right? So there are also some binocular cues. Binocular means we have two view here, and just like the motion parallax, with binocular view we can, for instance, the sand place here, then move during in these two. So for instance, this is left eyes, this is right eye. And for instance, we human can automatically find the matching between these two images. And for those have, say, the corresponding points move faster or have a larger distance. For instance, this is the delta here, delta 1 here, and we also have some corresponding here. When they have a larger delta here, say, for instance, delta 1 is larger than delta 2 here, and we human will recognize that, okay, this 12, the symbol here is closer to our eyes, and we will talk about this kind of topic in such a structure from motions in the later chapter. Yeah, and when we have these two eyes, and when you do your, say, for instance, if we have homework number 3, and you will try to find the correspondence, and you will get result like this one. Yeah. So some of students may be quite disappointed about this kind of thing. So okay, so we human can easily feel or predict a thing. However, why my algorithm or first step just get this kind of result? That is because some of our algorithm have some limitation. For instance, our stereo triangulation, and we rely on finding the corresponding to estimate the depths. And for instance, this one will correspond to another one. And sometimes it's difficult to find the correspondence. And sometimes some of the, say, the bush here, we cannot find the correspondence over there. So we will have some missing point here. And of course, nowadays we have some other technologies, such as we can do some depth filling or impending technology to fill this gap. But I have to say it, for the computer vision algorithm, there are usually have some limitations. So we have to combine various kind of technology to make our scene analysis better. Yeah, of course, recently we have deep learning may ease part of the work, but we still have, there are still some challenging tasks here. Yeah. And so let's go back to some history, and we will talk about uh, what we were taught, what we will teach in this course. Yeah, and because this is a first class, so I think we will not have a break today, and we will continue to teach or introduce all I want to introduce, and I guess we will not take the full 2 hours. Yeah, and let's after talking about the difficulty of computer vision, yeah, then we will go back to some history and let you know the evolution of computer vision. Yeah, so computer vision actually being applied in such as a military work or some industries in, say, a lot of study have started, say, in around 1970 or 80s. However, in the early age, it then can only do some limited work. Yeah. And for instance, in the early, in this case, this is aerospace photo or satellite photo for airport. And in early age, then usually have to rely on some, say, human tweaked filters. For instance, then try to analyze this kind of image, they have to, say, using some filter to find out some edges over there, and filter out some noise. Because when we use a camera, we'll talk about later in our chapter 1, when you really use some camera, of course nowadays we have some good uh, even nowadays we have some good cell phones, such as a camera such as iPhone or your Samsung camera. However, then actually use a lot of post-processing technology to smooth, say, someone's face wrinkle, right? And so for early age, if they would like to detect this kind of thing, then actually have to do a lot of manual tweak filters. So for instance, to filter out these plants, and then recognize and group them together to find then the plant, and then we have to figure out, for instance, there are some wing here. User defined that if we have two wings and we have a body over there, it could have a and at the airport, it could have a high chance to be a plant overlaid, and if you have some, say, house over here, roof overlaid, perhaps, or its definition is actually some square, tiered square overlaid or tiered rectangle. And if we have two of them, perhaps we can make up of a roof overlay, just something like that. Yeah. So in the early age, everything is manually crafted. That means human will define everything, and it is those manual craft solution is actually quite sensitive to noise or variation. For instance, your algorithm here could be applied for satellite image. So just like the satellite on Earth. However, it may not be applicable for such as the whenever we change the air conditions, such as the rainy day, right? Then it could be the algorithm will totally fail because when on rainy day you will see some cloud over there, and you will have some drop over there, raindrop, and they uh, will will ruin your algorithm. Yeah, so that is early age, and so however in that era, uh, or after 19th, there are some tasks and sex or computer vision has successful in some specific application. Yeah. So in the so what kind of environment it work better? So one of the typical idea is such as the plate detection, license plate detection. And for your, I actually have uploaded some of the PDF to the eStreet, and some of you may see there's a blank, a squared cover the image. That's because we do not own the copyright, and our school asks us to remove those unauthorized image. However, uh, we only we just use a block to cover the images. So if uh, if you know some way to remove those cover block, you can, yeah, you know that. Yeah. So anyway, so let's take a look at example. So in earlier work we have to apply it such as from the 90 to 2000. 90s to 2000, computer vision become applicable to some specific applications such as license plate detection. So why this kind of application is more easier to solve with computer vision? So that is because we have some we have some constraints for our targets. For instance, for license plate detection, because for instance, this is license plate, usually in a white background, and your character means your word, your number over there is constrained by the government, right, or DMV in the United States. Yeah, and so we can easier use some filter. For instance, we can use find the pixel intensity. Intensity means the, say, from 0 to 255. We will talk about later. For every pixel, we have a range, intensity range over there. Perhaps a simple idea is perhaps we can get pixel larger than, say, 200, and mark length and use some filter to mark those pixels. So for instance, we can get some regions with bright pixels, and we can also find some gradient. Gradient means we will find some difference. When the gradient means the difference between two pixels. Because the black and white is a strong gradient over there, then we can detect there are some intensive gradient over there, and whenever we find some solution to mix them together, we can get this one. Yeah. And so this is the way then, or a simple solution for license plate detection. However, there are some limitations. The first one is, for instance, we have to ask or require that our car plate have to be around the middle of the camera center. Yeah. For instance, the camera's optical axis over here, and then we have to say the plate have to be around these places. Yeah. And we also have to require our license plate to be cleared, and there's no mud or some other uh, uh, dirty things or some pollution over there. Yeah. Or some spot over there. Yeah. So again, you can see that there are some thresholding over there. Thresholding means some value can control some contents. So in this case, we use the thresholding 200 here. However, when your environment become darker, right, or become when we do that in the night, the number 200 may no longer work well. So you just have to put a light over there to light the plate. Yeah. And so in addition to the license plate detection, there is also another, I think this is a good and work through live computer vision. That is the AR marker. So that is called the AR toolkit. I guess there are some variations you may use recently. For instance, when you go to some museums, they also ask you to check some board over there, and even in uh, Nintendo and or some PS, they also have provided this kind of application using some idea similar to AR toolkit. So the idea is also then assume that there is a plate in the world, and the plate may have a strong white and black variations, and based on that, we can detect the contour of this plate, and we can also detect the corner here. And based on this corner, we can estimate the orientation. So that is the XYZ orientation. And with this XYZ orientation, we can put some virtual object over there. Yeah. So why is this successful? Just like the color plate detection, because then have predefined our target well, and so they can help us to make our result better. Yeah. And so that is around so AR toolkit is around, say, 1990, 1999, yeah, 1997 to 99, and after 2000, actually after 1999 to say 2011. Yeah, so that is an era for so-called the robust feature, because in the earlier era or early age or before 2000, we computer vision can only or work well in some specific tasks such as the license plate detection or some uh, uh, flow detection or the some spot or some uh, uh, say the industry uh, professional detection. So the the such as the imperfect spot detection, such as when you produce some clothes or produce some board, and then we can detect some or your the cover of your laptop. Then can use some this kind of sequential filter to detect some spot or flow over there. And however, those kind of process is only applicable for some specific environment or some specific, say the target. However, after the 2000, there are some new ideas to improve those conditions. That is called so-called we usually call that robust features or some invariant key points. So one of the most famous one is SIFT. That is called a scale invariant feature. So what is idea? Its idea is that if we hope that we can apply our vision technology to some general environments, such as this is a application of SIFT. For instance, this is Notre Dame, the 圣母院 in Paris, right? If you like to search, say, given this query image, we have to, if we would like to search some figures on internet to gathering together and even find the corresponding point to detect their view in the 3D do the 3D reconstruction. So we have to find some robust features. So its main idea is that we will talk. They're supposed to be your homework number 2 or 3. Yeah. So they have to define some way to resist some noise or the lighting condition. For instance, this is capture at dawn, and this capture at the cloudy day, right? And this is a sunny day, right? And their lighting condition different, so we have to figure out some good or robust features to resist to the change in colors, because for the same point, then actually have their intensity is quite different in these 3 images, right? So we have to find some robust feature, and we hope that it can also resist to some rotation, such as if we would like to detect the frog here, the frog is here, it could be occluded and the orientation could be different. For instance, this boy here, and its orientation is, oh sorry, this one is upward, upside, is rotates 90 degree, right? And so we have to figure out some robust features. Yeah. So that is one of the famous word called SIFT. That could be the most important or most big name before one of the big name before the deep learning. Yeah. And in addition to so SIFT is actually a manual, like one of the best manual means human create feature. Human craft means human crafted features. And around 2009 or 8, there's also another big name called DPM, which means in hope that they combine the feature estimation with some learning technology. Yeah. So the idea is if we would like to detect some human here, if we would like to detect some human here, then perhaps we can find some. We still use some robust feature. The robust feature, just like the SIFT here, we have actually, we will talk about later, is some orientation gradient. Means, for instance, if you have here, that is the gradient. Yeah. Then use the gradient and learn this kind of patterns. Yeah. And then not only for the whole body, and also decomposing to some, say, the head, some parts such as head, your limb, and your torso, and your leg, or something like that, and their relatively movement. Yeah. So then include the such as the robust feature idea with some machine learning technology, then substantially improve the potential detection uh, um, performance. Yeah, the person on street performance. Yeah, and I think recently you have known that after the 2012. Yeah. So the AlexNet. So I think most of you have learned the heard the stories. For instance, for CNN, recently big name, the CNN actually developed in say around 1990, but it's then can only train their networks through some CPU, right? And so there's no GPU over there, so the training is slow. So they can only deal with some limited data sets, such as the handwriting with say A to Z or 0 to 10, 0 to 9. However, with the LXNet, then can train such as the detect the big data such as ImageNet. ImageNet contains millions of image, and so after 2012, after LXNet, deep learning base will become the mainstream for computer vision. So there are several big names such as VGG, ResNet, GoogleNet, and others. So that is the evaluation of deep learning. So so in this course, what we will talk about, uh, uh, or what kind of technology we will talk about in this course. So first of all, we will talk about some essential idea about the camera and lens. And here is some example. For instance, may have someone of you may have the Sony's cameras, and there are popular iPhone and or iPhone Pro or Pro Max. For the modern camera, then actually composed of multiple lenses. So you can see that there are a lot of lenses over here. However, if you would like to uh, deduce some equation, if you use multiple lenses, it will be quite difficult, quite complex. So uh, for unless we will process some such as focus problem, otherwise usually for the first step is to uh, merge them together using such as a single lens to represent the compound lens. Compound means we have multiple lens. We can merge them together to be a ideal single lens. However, this is actually complex to calculate. You may learn some equations such as the focus in your high school. The estimation of or in your junior high school or senior high school. If you like to using this kind of lens model, uh, then work for some cases. But if you only want to estimate the depth or the things, this kind of model is difficult because they are nonlinear. Nonlinear means they cannot easily transfer to some linear problem. If we transfer something to linear problem, we can solve them by some metrics. Yeah. So just like a computer graphics, we usually use the so-called pinhole model as our most essential model for our camera. So this is our pinhole model. Yeah. So so in this course, first of all, we will talk about the camera and the pinhole model. And in the so this is the first chapter, and then this part was sort of like computer graphics. Yeah. So we will talk about what is the relationship between the light and the surface. And in your homework number 1, we will probably announce that 2 weeks later, because after work, some of students uh, may find that they are difficult to handle some metrics. So we can have some vacancy, right? Yeah, yeah. And anyway, uh, so for computer graphics, then probably have some surface here and then have some light here, then can render this kind of image. However, for computer vision, when we may do something reverse. For instance, given this kind of surface, we will estimate the surface undulation or the bump of the uh, relativity height of these models. So in your homework number 1, you may have this kind of say, for for instance, you have some such as scene here that we have lighting from here, lighting from there. We may use this kind of idea to estimate. For instance, this is the shape of Mickey Mouse. Yeah. And the surface from the image to estimate its surface. So this is usually called photometric stereo. Yeah. And we also sometimes the idea is sort of similar to shape from shading, right? Means we can estimate the shape from some lighting result. Yeah. And of course, every this kind of work have some limitations. Yeah, because we will talk about them later. So in this shift from shading or photometric stereo could be your homework number one. And because we will deal with some color, right? So we will also talk about some of the different of the color space, such as HSV or LAB color space, but we will just talk about which one is better, and but we can still use RGB space. Yeah. And I think the one of the important part of this course is talk about feature, and because they are from the early era to the robust feature, there are a lot of work talk about how to reliably or uh, how to extract some useful information from the image. So we will talk about such as age, corner, and to the shift, and some related other features. Yeah, and so the idea is that if we can find some robust feature, which means this kind of feature could be invariant in different view, and we can find some good correspondence. Given this kind of good correspondence, we may probably either track their motion or we can estimate the depth, right? And of course, you can see that sometimes this is the specular spot may uh, pollute or disturb our attractive feature. So this is the problem to deal with the real things. And for the last few uh, my last time to teach computer vision, my my homework number 2 is to say, for instance, given some random image here, not random, a scene, but the orientation is different. Student may have uh, to piece up, or you can say you can stitch those photos together based on such as a SIP feature. So writing a SIP feature by yourself could be difficult. So we may allow you to call some API to ease part of your work, but you still have to develop something. Yeah. And I guess 1 year our work is to piece up some, say, the lobby of of engineering building 3. That is our lobby of our department. And for given the camera photo here, you have to piece up multiple photo together. For instance, this is the elevator, and this is the LCD here. There's another door, and but not all. Some students may piece up 1 or 2 rounds, but for the further it will become slightly difficult. Yeah, so sometimes your score may be depend on how good you stitch your image. So that is homework number 2 in 2000 and say in 2016 or some other years. And then we will talk about the structure from motion. Structure from motion means, for instance, you have some view here, and we hope that we can reconstruction. First of all, we may have to estimate the rotation and translation. That is the movement between camera. And then we will have to reconstruction the depth or the scene. And afterward, we will, but later will depend on our time. We will talk about such as the clustering or segmentation, and I guess we will talk about if we have time, we will move to some of the recent learning-based methods. For instance, one of the typical one is the CPPS 2011 Shelton's work. For that is the use in the Connect for body tracking. For instance, and given the camera here, then can check your body, and you do not have to wear some such as the controller. You can get your bodies. So, but in that work that year, they use such as a randomized forest, some tree-like structure to detect our body. And after the recent years, we may have to move to such as using the CNN-like work or CNN-related work to, for instance, the famous Max RCN can get your region and detect your category. And of course, recently there are, in addition to CNN, there are such as the transformer, some new idea from the natural language processing, and they are also be applied to the say the image computer vision field. Yeah, and so but we because our goal of this course is give you a whole picture of the computer vision, and the robust feature is still applicable in industry or some uh, other things. So we may probably only have 1/3 or 1/4 of the time to talk about some advanced topics. Yeah. And uh, so how about the grading? Yeah. So in this course, we will have we're supposed to have one exam here, and but its percentage will be variant, and we're supposed to have one exam, and we will have 2 to 3 homework that is usually programmed assignment here. And the first one could be a photometric stereo, and the second one could be sieved related about robust feature, and the third one could be about the depth of the sync, and we will have a term project here. So we encourage you students, if you have some idea about computer vision, perhaps you can read some papers, and or your lab do some research, you can develop some research work. However, if you've not, you can take this term project as your homework number 4. We will give some of possible task for you to implement. Yeah. So but if you would like uh, to regarding the homework number 4, then you can only do that by yourself. This if you are a single person team, you may do some work assigned by hours. But if not, then you can choose to develop some project you are interested in. And but since there are a lot of people here, so I'm not sure whether we can present in class, but we actually have a synchronous video time, right? So perhaps we can make the proposal offline to become a synchronous video, but we will check how which way is better to use. And if we can go back to our classrooms, and we will sometimes we may invite students to discuss or chat your idea, and if you can get some good feedback, for instance, you have some good idea, perhaps you can get some bonus. And sometimes this could be included in the class participation, depend on uh, different kind of conditions. Yeah. And so this is the schedule here, and this is the beginning of class, and we will at least have 2 homework, programming homework, and we could have homework number 3 depending on schedule, and we could also have about the term project proposal presentation, and around the 2/3 of the semester we may have exam here, and at the end of this semester, we will have a final demo for your project or your homework number 4. So this is about the project and or homework number 4. Yeah. And uh, so this is announcement. So for the first 2 weeks, so that is today and the next week, we will use this link with WebEx for online course. And afterward, we will see whether there are new announcement from or a new instruction from our college or school. And currently, I'm not sure whether there are some students to leave this course, but currently in this moment we have 90% enrolled in this course. So that is the original expected upper bound. And but I know there are a lot of students required for add class. So I have discussed with our department and the college. Then say our upper bound is 110. This is upper bound. Yeah, the optimal upper bound. So so we have 20 quotas to add the class. However, and we also get some instruction from our college and department. The first one is because actually there's a new institute called 智能所. I am not sure what's its English name, and so there's called 智能所, and there is 智能所甲组. His required a compulsory course is computer vision. So and then also have some, because some of their student is were enrolled in February, so then do not have chance to take the course in January. So we will have to leave the 10 quotas for them. So that is assigned by our, so this including in this say 20 quotas here. Yeah. And so for another 10, so for another 10 quotas, so the first priority is, so if students from CS College and a PhD student for qualifying exam or qualification exam, so it will have a higher priority than students of the college, CS College, and also they also have a high priority. So that is 3 kind of person then have the higher priority. But I have to emphasize that. So for the 智能所甲组, currently the high priority only for those enrolled student. Means if you, for instance, you pass the you get your permission to this institute, but you haven't yet enrolled. Enroll means you have registered to the school. In that case, not totally belong to this kind of category. Okay, and so for student, you can go to attend this. If you still want to add this course, please you can go to this say this web page, just like which one? Let me check. Just like this one. So you have to attend these add course form, write down your name and student ID and some other things, and especially you have to register your current institute or your degree, and you have to write down your reason to add this course. And if you pass, not pass, if you are, so we will try to add as much people as possible, but whenever we reach the upper bound, then we have to let you know that we do not have quotas. Otherwise, we will directly add you to this course system. And so this course is English EMI course. It's English as a medium for instruction. So we'll be taught in English, and but students are still welcome to discuss and ask questions in Chinese. And for students, you can still wait or queue, waiting on the queue, because after we add the course, we will increase the upper bound. We will, after we process the echo add class, say, so please, if you want to register course, please do that before February 16, and we will probably announce the result around announce at February 17. And afterward, I guess some student may maybe when we teach some mathematics, metrics, some of them may be not interesting or think, okay, they are more interesting in computer using deep learning or some other things, and then don't want to learn some essential idea about computer vision. So someone will leave the course, and so you can still wait on the line, but I guess that is relatively fewer chances. Yeah, I know that is there are two people leave last week, and two people joined in this morning, I guess. Okay, so that is all I want to introduce today and this week. And I wonder whether there's other question. Yeah. Whether there are question from students. I will stop sharing the screen. Yeah. And if there's no further question, then we can stop the course today here. And if you have any question, you're welcome to stay here and discuss with me. Yeah. And if not, then bye bye.